All right. Thank you all for staying awake in sort of the peak nap time of the afternoon. Today, I want to talk about Coursera's approach to GraphQL, and actually Coursera's story of adoption, because I think it's a little bit different from most of the stories you've heard so far today, and how other companies have approached GraphQL. And I think that there's a number of lessons that we've learned throughout our journey that are useful to others. So, today we're going to trace through Coursera's adoption as we started from early days and REST APIs and how we've evolved our API frameworks to GraphQL, actually. So, imagine you're back in 2012. Coursera was just founded by two Stanford professors and with a mission to bring universal access to the world's best education. So Coursera, for those of you who aren't familiar, Coursera partners with the world's best institutions for higher learning and and education and high technology. We help them take their best courses from their best instructors and put them online and make them available either for free or for very, very low cost. Okay? And so I started at Coursera. We were, actually a very small, scrappy team sitting around a single table. There were like half a dozen of us, and we had sort of the basic in-course experience working okay. And then we were signing up courses and instructors and partner universities like mad, and we quickly discovered a problem of, hey, we need a directory, we need a catalog for all the courses that we had available. And our front-end team's like, guys, JavaScript, single-page apps, they're the way of the future. Let's use jQuery, it's gonna be great. This is the right way to build single-page apps. So myself as a backend engineer, like, fine. What do you need? And they're like, just give us JSON, REST-based APIs. This is the future. This is how we build apps. So, okay, fine. That's what we did. Our front-end team put together a JavaScript-based single-page app, and as a back-end team, we gave them all the JSON they needed. And when I mean that, I mean we gave them all the JSON. We had a fairly small catalog, and so we made one monolithic API that basically was the entire catalog, all the courses, all the instructors, all the universities, and we just served it in one single API call. And it was fast. Like, this was great. Our JavaScript developers could take all the data that they needed out of this API, display whatever pages they want, and they could iterate very quickly. So this was our home page, but that same API powered our catalog search page. And it was a super snappy experience because JavaScript would just run really quickly, and as you typed in queries, it auto-completed immediately. And this worked really, really great. We were able to iterate on front-end products and development, and we were decoupled between front-end and back-end. And this is actually a really great technology choice as we were getting started at Coursera. Until it wasn't. We actually fairly quickly ran into a number of problems, but they're not actually the ones that at least I initially anticipated. I thought that, the scale problem, sending the entire database essentially in one API request, I thought that was going to be what killed us. As it turns out, no, it was actually the fact that product needs change so rapidly at a startup in a company that's innovating very quickly. And very, very quickly, we realized that the APIs that we built just weren't flexible enough. So let me make this a little bit more concrete by some examples. We started introducing course sequences, what we call specializations. And our monolithic API, we sort of had to slam it in this sidecar manner because we couldn't change the existing monolithic API. It was dependent upon by too many individual JavaScript pages. We couldn't make a single huge change to refactor it how we wanted it. And so as we had specializations and identity-verified certificates, Signature Track, our premium course certificates, we sort of mashed the data in on the side, and that worked okay. It was hacky, but it worked. Unfortunately, the rubber really hit the road when some fundamental assumptions of our data model just got violated. So when we built our course catalog, we assumed that every single course was going to come from one and only one university partner. It may have a couple instructors, but one and only one university partner. And this was great. Up until two of our university partners said, hey, we want to collaborate on this course. And we were like, okay, so only one of you can be on the course catalog. And they're like, no. And we lost that battle real fast. That really started showing the frailty of this monolithic-based API approach that actually was serving us very, very effectively at the beginning. Additionally, as we were growing the size of our engineering team, growing very, very rapidly, we started stepping on each other's toes. Our front-end teams were actually able to iterate in parallel. They had the same data model, but they had different pages and different view layouts, and they could innovate as fast as they wanted to. But on back-end, when one team wanted to add that specialization data and another team wanted to add the premium course certificate data, we started getting these merge conflicts, and it was fairly tricky. We sort of figured it out, but this monolithic approach just didn't work so well for a single engineering team, given the nature of just one API, right? Then finally, eventually, by the end, when we retired this sort of architectural pattern, that number one point, the growth in the number of courses just was totally killing us. When we started, we only had a half dozen or a dozen or so courses. By the end, we have over 1,500 courses, and what we found is actually we were downloading over 1 megabyte of JSON just to display 12 courses on the homepage, which was absolutely absurd. I guess I want to take a step back and take some lessons from this first architectural pattern. And the key lesson is that scale matters. Scale matters a lot. Something that works very well for a small scale setup will absolutely totally fall apart at a larger scale. And conversely, a larger scale tool could be inappropriate in a smaller scale setting. But more importantly, scale is a lot more subtle than just big and small. In fact, it has a large number of dimensions. So what are some of those examples? One is queries per second. Coursera had a lot of users. Excuse me. Let me get this. Thank you. One example is queries per second. We had a lot of users browsing our homepage. We had a lot of users, browsing the course catalog, and we can scale up. We can scale horizontally, scale out, and that's a fairly easy technique. You want to use a different technique to handle scale of your data set size. You'll want to start sharding, and you'll want to scale across machines in a different sort of architecture and using different techniques. Scale also matters in the size of your engineering team. And so as we scale up our engineering team, things that worked well at small scale didn't work as well. And so we wanted to think about microservices and breaking up monoliths so that we could all work in parallel without stepping on each other's toes. But all three of these dimensions for scale are actually fairly easy. There's well-worn patterns and how you can solve them. The hardest one is what I would like to call the number of types in your ontology. And I think this is best understood with an example. So say we have a messaging application, this messaging application, you may have messages, and you may have threads, you certainly have users, and you may have likes or emojis or reactions or replies, but fundamentally, the number of types in your ontology, the number of entities or things, is only a small handful. And some products, some phenomenally amazing products, have very few types in their ontology. Some other products have a large number of types in their ontology. So at Coursera, in addition to having courses and specializations and instructors and university partners and identity verification and course ratings, we also have, that's just the out-of-course experience. You've got the whole in-course experience. You've got videos, you've got in-video quizzes, you've got assessments, you've got programming assignments, you've got forums, and you have actually underneath all of this, the authoring experience that our instructional teams use to actually put these courses on the course platform. Coursera is actually very much like an iceberg, that there's so much underneath the hood that you don't realize when you first approach it. And the number of types in our ontology just is absolutely killing us at Coursera. So we need to figure out how we were going to scale across the number of types in our ontology. And so the front end got their day in the sun. They could say, jQuery was the way to do it. And back end now wanted to put their own mark on Coursera's architecture. So we're like, microservices, guys, those are the future. That's how we should do everything. So we're like, okay, fine. We'll move away from this Python Django dictionary of lists of dictionary of lists of lists of dictionaries of dictionaries. We're going to get types. And we're going to get microservices, and it's going to be great. So what we did is we had sort of a mini competition where we built a service in Go, a service in Java, a service in Scala, and we eventually settled on Scala. We really wanted static typing to really straighten out our dictionaries of lists of dictionaries of lists of dictionaries of dictionaries of dictionaries. And we picked Play because it was a very powerful web framework, actually backed by formerly TypeSafe, now Lightbend, but the company behind Scala. We thought that this was going to be a great choice and solve all of our problems. In reality, we were sort of wrong. Scala was actually a good choice. The strong static typing discipline definitely did help us. And you see this reflected in GraphQL, and as we've heard all today, that static typing is actually really, really useful. But the flexibility of the Play framework was actually counterproductive. We didn't need that flexibility to control headers and body parsing and query parameters. We didn't need all that control to build an API. In fact, we wanted less control. We wanted something else instead. And so to really understand what we were actually looking for, you need to think about what is the whole purpose of an API. When you hire an API to do a job, what is its job? And its job is to get data from your server to your client. That's its primary job. It's not to be the most developer-productive system. It's not to be the latest technology trend. It's to get data from server to client. Coursera, I'm very proud of, has over 3/4 of its user population outside of the US. Most of our users are accessing, despite being a very young startup, most of our users come from outside of the US and access the course catalog and the course experience on 2G, 3G connections, and on mobile phones. And so as we were analyzing what are the performance requirements of our API systems, we decided on 2 key fundamental bullet points. And that is we need to minimize the amount of data transferred across the WAN. Again, these are very bandwidth constrained users. And additionally, we need to minimize the number of round trips. It was completely unacceptable for us to make one API request to get a list of course IDs, and then OAuth API requests to get the corresponding instructors for those courses, right? So we need to minimize the data transferred and minimize the number of round trips. And there are a number of nice-to-haves that help with both of those two, but those two are the fundamental key principles that we put as our performance baseline for our API framework. We scratched our heads and we thought about that for a while. And we eventually came to the conclusion that we had to go in one of 2 mutually exclusive directions. The first option is what is sort of known as experience-based APIs. And there are a number of companies that have gotten phenomenally good at building experience-based APIs. And what an experience-based API is you write one API exactly for your homepage, another API exactly for your course catalog and browsing page, another API for your course description page, another API for your partner description page, and another API for your specialization page. You just write one API for every single experience that you have, and it's perfectly tailored to exactly that experience, just the data you need, and only the data you need. And these would absolutely fit our one round trip and the minimum amount of data requirements. Unfortunately, we were a little hesitant to take the experience-based API approach. And there are a couple reasons for that. Number one is this sort of lends itself to a moderately tight coupling between the API implementation and the client views. And at Coursera, one thing that I've learned in my 4.5 years at Coursera is that we really have no idea what we're doing in terms of teaching online. There's so much innovation available to us. There's so many more improvements available to us. And it's a very exciting field, but it also means that stability is not something that we can afford. And so this tight coupling we felt was something that might be a little problematic. The second thing is that Coursera is a very young startup, and although we're growing very rapidly, we have very limited amount of engineering resources, and building a new API for every experience seemed actually fairly resource intensive from an engineering standpoint. So what's the opposite? Well, the opposite is a queryable API. Instead of building one API for every experience, you build one API, period. And every experience can query your API in whatever ways that it needs to get exactly the data required. And so we thought long and hard, and what does a queryable API even look like? Is it even REST anymore? And we realized that actually what we were really thinking of was a database. A database basically allows you to query it in many different ways, and you get exactly the data you need, and only the data you need, and you generally can do it in one round trip. And so we thought long and hard, okay, so what does a database even mean? And fundamentally, a database, at least a SQL database, and really a lot of databases since then, fundamentally comes down to relational algebra. And for those of you who don't remember your relational algebra from your database classes, there's basically 3 key points as relational algebra applies to REST or JSON-based APIs. So the first is projection. So if you have a table of courses, you can write a query in SQL to get just the course ID and the course name, and you can ignore or you don't get the very long course description that may be very, very large. Okay? So that's projection. You just want to filter the fields you get for every row in the table. Selection allows you to filter the number of items in your collection. So if you have a table of courses, you can get just the courses that have machine learning in their course title, for example. Okay? So this is like a search or a filtering. So this is selection. Finally, and this is probably the most sophisticated aspect, is joins. If you have a table of courses and you've got a table of instructors in an appropriately normalized manner, you want to be able to join across those. So you want to get a course, and you want to also get the instructor in one query, right? And so we thought long and hard, and so how does relational algebra make any sense in terms of REST or JSON-based APIs? And so this is what we came up with. Now, before I go a little bit further, this is all implemented on a framework that we call Naptime. So it's a little lightweight REST. Anyway, thank you for laughing. It's my horrible name choice, so I appreciate it. These APIs have been live in production at Coursera for almost 2 years now, maybe even longer. And you can actually hit these APIs right now if the Wi-Fi were to work for you. But fortunately, we don't have to rely on that to play around with Coursera's catalog APIs. So we have the courses endpoint, sort of the courses table, and we're going to now filter down to we want to get a single course, the machine learning course. And this is your query, and this is the response you get back exactly as JSON. And so that's how you can do selection within a collection. Now we talked about projection, and so what we call this is the fields query parameter, and so you can ask for the primary language in addition to this minimal representation you get back. And so you add the fields query parameter, and you get that exactly mirrored in the response. Very, very straightforward. So we talked about selection and projection. Now let's do the fun one, and that is joins. And what we call them is actually includes. So you include a related resource. So if you have a course and you want to also get the instructor for that course's instructor IDs, you add the includes parameter, and in the response, you get the related instructor in a single API call. Naturally, if you think carefully, this actually has to be fully recursive. So you need to be able to project across the related fields. And so this is the syntax that we use. So you can ask for the title of the instructor, and you get it in the response. And you realize that Andrew's most important qualification is that he was, of course, co-founder at Coursera. So we built this Naptime API framework, and that powers a lot of our APIs at Coursera. And we spent a lot of time thinking about it and building upon it. And this is actually what ended up happening. Even though we didn't force any of our developers to move away from the stock play framework APIs, we found that all of them radically preferred using Naptime. So the blue line is the rapid adoption of Naptime within Coursera by the Coursera developer community, and you can just see a complete stagnation in terms of using the play framework. And we saw this success due to a lot of iterations. You'll notice, actually, one important thing I should point out. We started far before Facebook started talking publicly about GraphQL. But some of you may have noticed that a lot of the same lessons apply right back and forth. And that's an important part of our story. Anyway, developers adopted Naptime in droves. But in order for us to support that, they didn't immediately take off. We spent a lot of time iterating on our APIs, and we had a number of important lessons that we learned. And so taking a step back from our story, we learned that you have to meet your key performance baseline requirements for your API framework. That's table stakes. But then after that, you want to optimize for developer productivity. This is absolutely critical. And we learned a lot in terms of what is the best way to optimize for developer productivity. First and foremost, we realized that it's incredibly important to use static typing. It's absolutely not possible at Coursera's scale of ontology to do everything in a dynamically typed manner. You need tools to help you help developers move from different parts of the code base without needing to spend a whole bunch of time reading documentation. And so the Naptime API framework actually catches a huge number of potential bugs and API inconsistencies at compile time. In addition to that, in addition to ensuring that all the APIs look and work and behave the same manner, so that it's not a convention but rather enforced by the compiler, the Naptime framework also allows you to use arbitrary data types, or ADTs, in as many possible places. So it's not stringly typed. You can use arbitrary sophisticated types, and that was very important. Now, to enforce all of these constraints and make this all work, we actually leverage a large number of Scala's advanced language features. We use macros, we use path-dependent types, we use implicit type classes. But you have to leverage these features very, very carefully in order to not make it impossible for new developers to learn your API. And so it's very important to leverage types, but it's very important to leverage them carefully. The other thing that we learned is that you shouldn't model these collections or these tables as a single sort of blob for each element. It's very important to leverage things as a collection of key value pairs. Everything has an ID, and everything has a set of fields that correspond to the value. You'll notice this is very much the same thing as what Relay encourages you to adopt with the ID pattern. We came to the exact same conclusion as we were building out our Naptime APIs. In addition to making the types work a lot more nicely, it also very much makes it easier for developers to reuse code in different areas. This one was perhaps the most surprising of all. An opinionated framework improves communication. What we found is that after developers used one Naptime API, they'd learned them all. And what this meant is that front-end engineers would be able to talk to a back-end engineer and say, hey, I need a finder with this query parameter that is joined to this other resource, and in a very succinctly straightforward manner, by having a strong opinion, having a strict ontology for how your APIs look and feel and work, makes it so much more productive to communicate. No longer were you bike shedding about, where should this be a query parameter, should this be a header, should this be whatever. No, it's very straightforward. You'll have a great way of doing things. And so this is what led to Naptime's radical adoption within Coursera. Now, despite saying that Naptime cured cancer and solved all of the world's woes, unfortunately, a number of problems still remained. The server-side API worked really, really well, but me as a back-end developer, I wasn't able to really handle doing the right thing by way of our front-end developers, our mobile developers, and our web developers. And so we had a number of problems. So that flattened representation where the related resources are flattened in a list, although it does mean that we can potentially eke out slightly better network bandwidth optimization, in practice, it was just very difficult for clients to then rehydrate back things from that flattened representation. Additionally, the URL syntax ended up being fairly difficult for developers to maintain over time as we were evolving APIs and products. Extra fields ended up getting left in there. Some developers, were very confused as to where to add stuff, and it was just very cumbersome. And finally, although Naptime captures a huge amount of information statically at compile time with its type-safe manner, although we were able to get very sophisticated and detailed schemas from our APIs, we never were able to fully invest in a documentation or client-side tool. Naturally, when we heard about Facebook talking about GraphQL and we saw graphical, we realized, hey, this actually fits together really, really well. This takes the weaknesses of the Naptime framework that we use internally at Coursera and couples it with an open source project that fills in those weaknesses, addresses those gaps, and is the right way going forward. And so we saw GraphQL is very much on the horizon and very much dovetails with the way that we do things at Coursera. So let's actually take a look at how close they actually are. So this is our first query on the courses resource, and here you can see it translated in a very natural fashion into GraphQL. And as you add fields, they show up appropriately, nested joins and includes, again, very straightforward, and of course it works recursively. So we realized, actually, instead of trying to dump everything that we've already built, these well over 700 different APIs and resources, actually, each one having multiple APIs themselves, why don't we define a bijection, define a translation layer between our current REST APIs, REST and JSON APIs that we use and know and love mostly, and GraphQL, the direction that we want to go. So this is a quick look at our architecture. We have an edge tier that handles DOS, DDoS protection, as long as you're not dying, and routes requests to the backend distributed constellation of microservices. We've got like 50 different microservices, each handling different subsets of the Coursera platform. And so this is how requests work today. And so we're introducing this assembler service. This assembler service, requests will come in from the edge tier, GraphQL requests will come into assembler, and assembler will then be able to farm out requests to the backend services. Now, one thing that's very important for GraphQL is that you have one unified schema that lets you join across all the arbitrary types. And so the way this ends up working, I think it's best illustrated through running through an example together. So let's say we have a GraphQL query that comes into the assembler service, and we need to get the user's profile and the course title and the instructor for all the courses that a particular user is enrolled in. So the assembler will say, aha, I'm going to query the profile service to get the user's profile. Once I've got that then tells me what information I need to go query from the enrollment service so I can get the list of courses the user is enrolled in. From there, the assembler service can actually send a fat query, a larger subset of the GraphQL tree, to the catalog service to fetch both in one request the list of courses and their related instructors. Right? So this is a distributed GraphQL implementation where GraphQL can be evaluated at any different point. The assembler service just handles across the different services joining things together. The other thing that's interesting about this is that each of the different backend services exposes their own GraphQL subset of the GraphQL schema. And the assembler service aggregates it all at runtime and exposes that one unified schema available to all clients. The other thing you'll note is that because everything is just actually adding GraphQL, adding this bijection layer is additive, this sets up an incredibly smooth transition plan for us at Coursera, just because GraphQL and Naptime, our own internal learnings, are so close. So what we're doing with our clients is they currently use the existing REST, JSON, Naptime APIs, and instead we're going piecemeal by piecemeal and migrating them over to GraphQL. Backend developers will absolutely continue to write their APIs in Naptime, and the backend APIs that the backend developers write can be used either directly as REST JSON APIs or through GraphQL without any single code duplication. So not a single backend developer besides myself and my colleague Brian ever write any code for the assembler service. Every backend service has their own GraphQL schema, and it all gets aggregated dynamically at runtime. So we have this all working together in production. This is a screenshot from Graphical, a phenomenal tool that, of course, you all know and love. And this is it working against our production schema that has thousands upon thousands of types, and if you print it out, is well over 10,000 lines long. We're working on migrating 100% of our client data access, almost. Nearly 100% of our client data access to GraphQL by the end of 2017. We're all in on GraphQL. We are convinced that this is the right way to be building technology this time in 2016, and maybe even 2017. Taking a step back from this story, what are the key lessons, or rather some more key lessons that we've learned throughout this journey? The first is to carefully understand your problem. We did not appreciate the subtle nature of scale at the beginning of our journey. We didn't realize that the solutions that work well for scaling the number of engineers don't inherently work in scaling the number of types in your ontology. When we thought that the play framework was going to be the right solution for us, we were only half right. And so whenever you encounter a problem, don't just take the latest shiny new tool. Think carefully to understand your problem and what's going to be the right solution. While you're thinking carefully through your problem, it's also very important to look to history. As much as we love to make fun of the latest trends and both make fun and use the latest trends in technology, as it turns out, a lot of the problems that we encounter have been solved before in maybe a different form. And so APIs and relational algebra actually dovetail very, very nicely. And so it's always important to look to theory to stand on the shoulders of giants that have gone before us. Finally, and perhaps probably one of the most important things is it's very important to plug into the ecosystem. We were developing Naptime on our own, and we got pretty far, but we definitely couldn't build anywhere near as complete of a solution as we can joining in with the rest of the GraphQL community. And so it's very important to plug into the ecosystem wherever possible because it's much better to work together. And so I want you all to know that Naptime is developed in the open. We send each other pull requests right in the open. You're welcome to join in. We'd be happy to have you either use our system or contribute back to it. We think it's a really great system. We've spent a lot of time optimizing it, making it work very well. Of course, if you want to take the next step, if you'd like to join the team at Coursera, building what we think is going to be the best learning platform for education at scale, we have a lot of really fun challenges and problems to work on, and we'd love to have you join us and join the rest of the team. With that, thank you.